started. So what we're going to do is find the directional derivative of the following function. We have f of x, y is equal to x squared plus y cubed in the direction of, and I'll give you a vector here, of v is equal to 4, 3, okay? And then we're going to say at the point, I'll give you a point as well, 1, 2. Okay, so let's make sense of what we have. We have our function, first of all, that's our multivariable function, okay? And then this is our direction vector, okay, that's where we want to point, and this is our point that we want to evaluate it at. So P is equal to AB, so A equals 1, and B equals 2, okay, for our formula, for the sake of our formula. And so let's write down what we know about directional derivatives, how to compute it. So D sub U of F at AB is equal to the gradient of F evaluated at AB, and then we're going to dot that with the direction vector divided by its magnitude, right? Because this is our unit vector that we want. Okay, so first of all, we just had to find the different components and then just plug it into the formula. That's basically what we're going to be doing. So first of all, let's find the magnitude of V. So we have that V, our direction vector, is 4, 3. So to find the magnitude of it, we just square the components separately. We're going to add them together and then stick a square root sign over them. Okay, so this is going to be 16 plus 9, and that would be square root of 25, so that is going to be a 5. Okay, so this will be a 5 down here, so we're going to keep that in storage for later. Okay, so we'll keep that piece of information. And now we do know V already, so that's all done. We know that that's 4, 3. Okay, and we finished that. Now all we need is the gradient of F evaluated at AB. So let's find the gradient of F. So gradient of F. That's going to be, the gradient is obtained by taking the partial derivatives with respect to each variable. So the first one's going to be f sub x, and the next one's going to be f sub y, and it's only a 2-variable function, so we only have 2 components for a gradient. Okay, so the first one, if we differentiate this with respect to x, the y goes away, and we just get a 2x. Okay, and then for the second part, if we differentiate with respect to y, then the x's go away, the x term goes away, and we just get a 3y squared. Okay, so here's our gradient, right? And now what we have to do is evaluate it at our given point AB, which was 1, 2. Okay, so now what we're going to do is just plug that in. So we have the gradient of F evaluated at 1, 2 is equal to 2 times, and then for x we're plugging in a 1, and then we're plugging in a 2 for the y spot. Okay, so that's just going to be a 2 and then comma 12. Okay, so this is our gradient, right, evaluated at that point. So this is going to be our gradient of F evaluated at 1, 2. All right, so now we have basically all the pieces of the puzzle to plug in, and I will do so on the next slide. Okay, so again, our directional derivative of F in the direction of U at AB is going to be, I'll write down the formula again before we plug everything in. So at, actually at 1, 2. Okay, so I'll replace that real quick. So of F at 1, 2, there we go. So that's going to be the gradient of F evaluated at 1, 2. And then we're going to dot that with whatever our direction vector was over the magnitude of that direction vector. Okay, so this is going to be equal to, what we obtained was 2, 12 for our gradient there, remember? And then we have that dotted with 4, 3, and then this is all divided by a 5, right? That was the magnitude there. So what I'm going to do is just move that 1 over 5 out in front so we can deal with it later. And then we have, if we take the dot product, we're going to do 2 times 4, and then plus, this is a 12 times 3. Okay, so this is 1 over 5 times 8 plus 36, and that's going to be 1 over 5 times a 44. Okay, so our final answer is going to be 44 over 5, also known as 8.8. Well, maybe not also known as, but the calculator knows it also as 8.8. Okay, so that's basically it. And again, the directional derivative tells us the slope of the tangent line at the point P. So this would be at the xy point 1, 2. Okay, so at that point, the slope of the tangent line is 8.8 or 44/5. And this is created by forming the direction of the tangent plane. I don't know what that looks like, so I'm just not even going to try to draw it. But anyways, so this is the slope of the tangent line obtained when you're on the vertical trace curve, when you form the vertical plane through U on the xy plane. Anyways, so yes, so our answer is 8.8 or 44/5.